All right, chapter 3 is motion in two dimensions. Previously, we did motion in one dimension, so we went back and forth. Now we can go back and forth, up and down, etc., etc. Does it get to three-dimensional? Yes, but we don't do that in this class. Another term for motion in two and three dimensions is projectile motion. Um, with the two-dimensional motion, all the equations from chapter 2 are going to be used, except they're going to be with respect to an x or a y. Meaning, if I come down here, from last chapter we had x is equal to v naught t plus 1 half of at squared. To truly make it in the horizontal, i.e. in the x, it'll be x is equal to then v naught xt plus 1 half of ax t squared. This is then only for then horizontal motion. Now, note, in free fall, your horizontal acceleration is going to be 0. Meaning if I go back up to this little picture and it shows Mr. Bird, and Mr. Bird's going to go poop on, I guess, those people over there, the horizontal velocity, notice that it starts at 9.44, and a few moments later it's still at 9.44. There's no horizontal acceleration because gravity is always going to act up and down, not side to side. And so, coming back to here, what that means is your x equation in free fall will collapse to just x is equal to v naught xt, which you'll recognize as, oh, I'm going to put parentheses around this so that you guys know that v naught x, it means v velocity at time 0 in the horizontal direction. That is simply just rate times time equals distance, this equation. And then likewise, your y equation now becomes v naught y t plus 1 half ay t squared. And very similar in free fall, and not all of your equations are going to be in free fall, or problems, I'm sorry, but most of them I believe will. And when you're in free fall, your ay is generally equal to g, which is then equal to a negative 9.8. So this is your first instance with the letter g. G is the acceleration of gravity. Note for later chapters that g is just equal to 9.8. This is the actual value. It's always going to be a positive 9.8, but we make it negative. Where am I thinking go? We make it negative to denote that it's pointing towards the center of the Earth. So the value of g is actually a positive thing. So, and that's going to come later on, but I'm just pointing it out now just to hopefully get it ingrained in your brain. Some other equations we've got. We had v squared is equal to v naught squared, that's not squared, plus 2a, and I wrote delta x. Well, in the y, this will be vy squared is equal to v naught y squared plus 2ay delta y. So, all the same equations. Oh, one more. We have vy is equal to v naught y t plus ay t. Yeah, sorry, wrote that in there. So, same thing, it's just respect to one variable over the other. Now, how do we put this kind of into practical use? So let's give us a problem here. Let's say I roll a piece of chalk off of a 1.2 meter table. That's about the height of the table in room 104 where I normally teach this class. It doesn't really mean anything doing this online, I guess, but that's the height of the table, so I always use that as an example. Initial velocity of 9 meters a second. It's like 20 miles an hour. It's not unreasonable. We're going to figure out how long it takes to hit the ground, how far horizontally will it travel, and where relative to the floor is the marker located at 3 seconds. Sorry, 0.3 seconds. So I'm going to draw a pretty little picture. You're going to have to draw lots of pretty pictures. It doesn't necessarily have to be pretty, but it needs to be a picture. Mine are pretty. Why are they pretty? I don't know. I just like to tell myself that, I guess. So it goes, and it goes, bam, it hits the ground. So, a couple things I know. We need to figure out how far this horizontal distance is, x, At some point, I'm going to have to, well, I already know, but I'm going to have to use it to figure out how far it's fallen at a certain point in time, and this is called y. And what do I know? I know that when this marker leaves the table, it's going to be directly horizontal. So I'm going to write that down because that is important to know. Directly horizontal. Horizontal, okay? Horizontal. Alright. Basically, well, let me do it this way. Alright, so here's my table. It's kind of a side note here. What if it actually didn't go horizontal? What if it went at some angle above the horizontal? Now we get to use our trig, and that's a really bad arrow. That's better. Okay, so kind of like in chapter 1 where we had to find maybe the horizontal and vertical components, this is going to be the same thing. Basically, if it were to leave at some angle, I will call theta. Then, oh, it's a bad theta, you say. Yes, you are right. It is a terrible theta. That's a better theta. Then your initial velocity is going to be v naught. V naught is your initial velocity. That's what we're going to have to project. What do I mean by that? Well, there are two components of your velocity. You have a horizontal component and a vertical component, v naught y. And so, what you're going to have to do under normal circumstances, and I'll relate it back to this being horizontal in a little bit, is each time you might have to find your components of the velocity. To find your v naught y, to find your v naught x. Well, how do you do that? Well, I noticed a couple things here. We have v naught sine theta, v naught sine theta. V naught's my hypotenuse. Sine theta means the opposite side of where this angle is. Well, opposite to that is my v naught y. And likewise, v naught cos theta. Cos means next to. There's only one thing next to this, and that's v naught x. So we have v naught sine theta, v naught cos theta. This is what we're going to have to do nearly every problem. I start off kind of simple, directly horizontal, because, well, why is it simple? Well, so if this were to leave it, let's say this is 30 degrees, then we would do v naught, whatever that is, sine of 30, v naught cos, whatever that is, 30, okay? But it's not 30. If it comes off directly horizontal, your theta is going to be 0. And so this is kind of maybe like a trig review, but I know that my initial velocity is 9 meters a second. So to find v naught y, I would say 9 meters a second sine of 0. Well, if you remember your trig, the sine of 0 is 0. And then, okay, well, v naught x is then going to be 9 meters a second cosine of 0. Well, cosine of 0 is 1, so it ends up just being 9 meters a second. So when it's directly horizontal, that means all of the initial velocity is going to go and be directly converted to the vertical velocity because your initial angle is 0. The higher your angle at 45, it's going to be the same, your v naught y and your v naught x. And if we get to 90, it would be completely vertical, and the cosine of 90 gives you 0. So basically put, kind of going back to this little sketch of the little birdie, is that you have no initial y velocity here, but as you go down, your y velocity gets larger and larger, or your vertical velocity. Meanwhile, your horizontal velocity, just in the bird problem, will always stay the same because acceleration is only going to act up and down. So, anywho, kind of a long side note to this problem on why directly horizontal is going to be 0. This will kind of get in more ingrained as I do more problems, but I figured I should at least start with that. So, alright, let me come over here. Now that I know all this, I need to, start the problem. I want to know how long will it take to hit the ground. Okay, so your first step in any type of projectile motion problem is to find the time. Well, you have two equations, well, lots of equations, but if we want to know uh, horizontal distance, it would be x is equal to v naught xt. Remember, it's v naught xt because we're in free fall, so acceleration in the x is going to be 0. So if I roll back up to there, that's why we got this equation right here. Okay. Well, the problem here is I don't know horizontal distance for my cursor here, and I don't know time, so I can't use it. So then I use y is equal to v naught y t plus 1/2 of ay t squared. Okay. We know that v naught y is 0 because it was directly horizontal. So that's going to give me y is equal to 1/2 of a sub y t squared. And we know that y is, this is how long it take to hit the floor. If I scroll up here, I know it's a 1.2 meter tall table. So I should probably note that I'm a little picture here. Let's just take you out. You're just going to be 1.2. That's what you are. All right, there we go. And I make it negative, kind of like last chapter. We make it negative to reflect that you're displacing downwards. Displacing is a word. It is today. All right, so equals 1/2 of a negative 9.8. I make it negative to denote that it's pointing towards the center of the Earth. T squared. Get rid of my negatives. Be positive, Pete, both sides around. Oh, and meters cancels out too. Let's get rid of the negatives. So that gives me 1.2 is equal to 4.91 per second squared, because I got rid of the meters. T squared. And so I need to solve my equation for time. 1.2 divided by 4.9. Raise that to the half power. Gives me 0.49. Yeah, 0.49 seconds. We'll leave it at that. So I know it's going to take 0.49 seconds. Let me erase all this riffraff. I don't know what riffraff is. It's this, apparently. It's going to take 0.49 seconds for my marker to roll all the way off the table and hit the ground. So, the time in the air is 0.49 seconds. To figure out how far horizontally it's going to travel, I use x equals v naught xt. Coming over, there's my cursor, here. So, x is equal to v naught xt to get horizontal distance. X is what we're looking for. V naught x, remember, is just 9. T. And, oh, well, I wrote that in there, but I already know what T is. How? I know it's 0.49 seconds. Oh, but that's like completely something different. You say, well, yeah, it kind of is, but it's not. Remember that the time it takes for the marker to hit the ground, oopsie, is the same time it's going to take for the marker to go horizontally. So if you find the time in one direction, you can use it in all directions. Yay. So that's why I use that. And so that's a point, by the way, not a negative, just in case you get curious. Because it did come with like a negative, weirdly. All right, then times 9, and that's going to give me 4 point, I'm going to round it to say 4.45. Therefore, neglecting air resistance, the marker will travel 0.45 meters. And then my last part of the problem says where relative to the floor is the marker located at 0.3 seconds. So I am going to erase some of this brouhaha. Changed up my vocabulary. I learned brouhaha when I got it from a dictionary once. What dictionary you say? Well, I had a job that was so boring I used to read the dictionary every day. And brouhaha was one of the words I came up with. And like, oh, this is cool, or I'll use it in a sentence. Still been using it since. Anywho, alright, so that's erased. And I want to figure out where it's going to be located at 0.3 seconds. So I'm going to kind of redraw what I had. We know that all the way down was a time of 0.49 seconds. So basically, I kind of want to figure out where it is here at 0.3 seconds, because it's not at the start, and it's not at the end, but it's somewhere in between. Well, how do I do that? Well, I need to find first how long it takes to get there. Um, and since I want to know height, I'm going to start with the y equation and not my x equation. There we go. So, y is equal to 0, remember, plus 1/2 of ayt t squared. All right, well, I'm looking for y. This time I know the time. That's a negative 1/2. I pulled it out front because that's from my acceleration of 9.8. And then my time is 0.3 seconds, and I need to square my time. So, let's see here. 1/2 of 9.8 times 0.3 squared is going to give me 0.44 meters. And actually, it's not just a regular 0.44, if you've noticed. It's a negative 0.44 meters. Meaning, it gets displaced. I'm going to erase this part right here. It gets displaced 0.44 meters from the start. So we want to figure out how high off the ground, because it says where relative to the floor. And so I know it starts from 1.2 meters. And I know it's going to drop 0.44 meters. And so that's going to give me, what's that sound like? 0.76 meters above the ground. So, a lot of different things about one problem. Not every problem is going to have this many steps, and I'll do other examples, I promise. Like right now. I used to have this problem a little bit easier, but I decided to make it slightly harder because it kind of matches one of your homework problems. So hopefully that's going to be more useful to you, but it is what it is. So, baseball player. Tall baseball player, because that's actually pretty tall, the shoulder height of 1.8 meters. Hits a ball with a velocity of 48 meters a second directly horizontal, so a true line drive. By how much will the ball clear a 1.2 meter tall fence 5 meters away from the players? Why is he near a fence that short? I don't know. Yeah, I can't answer it. Can't answer it. But he was. At least in my problem he was. So, alright, let's go draw a pretty little picture. He's a baseball player. He's got a bat. It's a bat. Yeah, there's my bat, he says. He looks like he's running, because that's how he hits a baseball. Didn't know that's how you hit baseballs, but apparently it's so. It's going to be a line drive. And it's going to clear some fence. Right there. And then it's going to eventually hit the ground. Okay, so baseball player hitting it. I know that my baseball player is 1.2. Ooh, really close to the edge there. And then I know my fence, I think, oh, whoopsie, 1.8. Yeah, you probably caught that, didn't you? I didn't. Oh, I didn't. 1.2 meters. Okay. All right. So he hits it directly horizontal. Remember that I said, and I'll redraw this here, if we hit it at an angle, we'll have our initial velocity v naught, and then we'd have two sides of our triangle, our horizontal velocity and our vertical velocity, v naught x and v naught y. In this case, this inner angle right here, theta is 0, and so we would have 45 meters a second sine of 0 equals 0 for Vy, or V naught y, I'm sorry. And then 45 meters a second cosine of 0 is equal to, well, 45 meters a second, because cosine of 0 is 1. Okay. All right, so we know our components. We want to know basically how much will the ball clear a 1.2 meter tall fence 5 meters away. So this is a little bit different. We know this time our horizontal distance. We know that the fence is going to be 5 meters away. So since I know my x, and since I know my v naught x, I can use x is equal to v naught xt to get my time it takes to drop this little amount. See, it's a y. There we go. This little amount to see how much it's going to clear the fence. So I'm going to do that. All right, let's do that. 5 meters away equals 45 meters a second times t. And so you take 5 divided by 45 and you get, what looks like 0.11. So it's 0.11 seconds is how far it's going to, or how long it's going to take, or the time it takes to, 0.11 seconds is the time it takes to travel 5 meters horizontally, and we're also going to figure out how much it dropped during that time. There we go. And so I need to use now my y equation to figure out how much it's dropped. So it says y is equal to 0 minus the 1/2 of 9.8, since I know that gravity is going to be negative, pointing down towards the center of the Earth. And now I use the time that I just found, 0.11 seconds, and I square it. And so I get y is equal to a negative 0.06 meters. So that means it's been displaced 0.06 meters. So it started off at 1.8 meters. It's been displaced 0.06 meters. And so you take your 1.8 and you subtract your 0.06, and I'm going to round it to say it's going to be 1.74 meters. But keep in mind, going back to my old picture, all I did was figure out the height of it. It's the absolute position. Excuse me. Absolute position relative to the ground, and that's 1.74 meters. But I want to see how much it cleared it by, right? So then I say, okay, 1.74 meters minus 1.2 meters, and that's going to give me 0.54 meters. So it's going to clear the fence by a little over 1/2 meter. Even without air resistance, or with air resistance, I'm sorry, it's probably still going to roughly clear by about that amount. Most line drives are not really line drives. They actually have a little bit of an arch to them, because a pure line drive really doesn't even clear the infield. Because if it's hit directly horizontal, I mean, most people really aren't that tall, so it's not really going to go very far. So yeah, another horizontal one, but they're not all going to be horizontal, as exampled in this one. So I have my two made-up nations are at war just because, I guess. We got Pizzanen in Tacoiria. Pizzanen and Tacoiria at war. Pizzanen launches a mortar round at 250 meters a second, 32 degrees above the horizontal. So now we got an angle. How far horizontally would it travel? Neglect the Marine's height. So basically put, we're launching something at an angle. Ooh, that's a really bad arrow. Oh, and I made marks below that. How sad. Okay, keep going here. Oh, lost it. Excuse me. Okay, so 250 meters a second. That's our V naught. That's going to be this side of my triangle. We need to find the vertical velocity, V naught y, and the horizontal velocity, V naught x. So V naught y, if you recall, is going to be V naught sine of theta. And V naught x is going to be V naught cosine of theta. But this time we have an angle. Oh, yes, we do. So V naught y is going to be 250, and that's a reasonable value. I actually looked it up on this. sine of 32. Make sure you're in degrees. And that gives me 132. I'm just going to say 132. Oh, let's do 132.5. V naught x is then going to be 250 cosine of 32. And that gets me 212. Did I leave myself room? No, guess not. Okay. So I want to figure out how far horizontally it's going to travel. There's a lot of different ways I can do this. I think I'm going to do this the long way the first time, and we'll leave a shorter way here in a little bit. So, going back up to my picture, well, redrawing it. We will employ something that we did last time, i.e. from chapter 2. We know that at the very top, it's still going to have a horizontal velocity of what? 212, because that never changes because acceleration only acts up and down. But we know that the vertical velocity will be 0 at that point. Otherwise, we keep going up forever. Sorry. So, what I need to do is figure out the time it takes to get to the top. If I can figure out the time it takes to get up, I'll call t up, I know that's going to be identical to the time it takes to go down, t down, because it's a perfect, well, parabola. So, what I need to do is figure out the time it takes to go up. Okay, well, let's use our Vy equation. So Vy is equal to V naught y plus Ayt. So 0 is equal to a positive 132.5 meters a second, since the vertical component's going up, minus the 9.8 meters a second squared for gravity, t. So I take my 132.5 and divide that by 9.8, and I get 13.5 seconds, which is a lot of time. But this is pretty fast too, so makes sense. So, the time it takes to go up would be 13.5 seconds, and it would be identical to the time it takes to go down. So if I want to get my time total, my t-tot, like a tater tot, only probably not as tasty, I just take 13.5 and multiply by 2 to get 27 seconds. So, this is 27 seconds of air time. It will be in the air for 27 seconds. To figure out the horizontal distance, I can use my V naught x t equation, Fox t. So I take my x, or rather my V naught x, my 212, I think I just said 212, I didn't round it to anything special, and I multiply that by 27 seconds. So 212 times 27 will give me 5724, an extreme number. It'll be a little bit less than that because of air resistance, but there, 5724 meters, or we would probably express that as 5.724 kilometers at that point, given how far it is. Note that I could have found the time it took to get, the horizontal distance it traveled in the first part, and I could have doubled it just as much and just flipped the whole thing around. That would work. This isn't the only way of doing this. There's about a million ways of doing some of these problems, but this is the way I chose to do it at the time being, so yeah. Well, there's going to be retaliation, because Taqueria isn't going to, it's not into pizza and, going after them and dropping pepperoni and sausage bombs. So Taqueria drops a bomb. I mean, it doesn't launch a mortar, it just drops a bomb from a plane at around 3 kilometers, traveling at a horizontal velocity of 120 meters a second. The bomb will glides until it's detonated around 200 meters above Pizza Hut's capital city, Little Caesarsville. How far away is that capital? Okay, so I got to kind of show you what's going on here. I'm not very good at drawing a plane, so I draw a bird. Beautiful bird. Okay, it's not a. That's still even a terrible bird. Terrible bird. All right, I'll draw a plane. Just not good at it. Meow. Meow. Ew. Cockpit. Actually, that's not bad a plane. Except this little wing is not really proportional. And it's going zoom, zoom, zoom. Okay. So the plane was traveling directly horizontal. So when it drops a bomb, that's my bomb. It's not a very good bomb. It's also going to be traveling directly horizontal. And then the bomb is going to glide and glide until they detonate it 200 meters. So what I said, above the ground. So, what do I know here? Well, my V naught X, since it's horizontal, is simply just going to be 120, as it has been 2 of the previous problems we dealt with. And it will have no vertical component, because when you drop a bomb out of the plane, you don't push it out, you just drop it. And it's not like a self-guided missile that's got some sort of inward thrust to it. No, just dropped. Just dropped. Okay, so we drop our bomb, and we're going to detonate it 200 meters above the ground. And that's a really bad 200 meters to the point where I can't read my own writing. And when I can't read my own writing, then I make mistakes. So let's read our own writing. Okay, so I know it's 3 kilometers total. So then the displacement that it's actually going to be is going to be 3,000 minus 200, 3,000 being meters, 2,800 meters, or 2.8 kilometers. So my y is then negative 2,800 meters. Okay. We want to figure out how far it is away, because when you drop a bomb out of a plane, you have to drop it before you get there, especially how high you are. Because you got to account for how long it's going to take and its initial horizontal velocity, which is going to be the same as your plane, and where it's going to. You got to basically peg it to where it's going to land. So you're going to have to drop it beforehand. We want to know how far that distance is, x. So, I think I left myself room. I did not. Okay. I can't use x is equal to v naught xt because I don't know time and I don't know x. So I can use my y equation. We have y equals 0, because v naught y is 0. Minus 1/2 of 9.8. And I already know what y is. I'm going to plug it in a second. Meters a second squared, t squared. And my y value, which I forgot to write in here and I've already figured out, is negative 2,800. So, simplifying and being positive peats. It's going to give me 2,800, canceling out my meters, canceling out my negatives. It's going to give me 2,800 is equal to 4.9 t squared. So 2,800 divided by 4.9. Raise that to the half power. It will have a lofty air time of 23.9 seconds. So then we need to figure out the horizontal distance. So we have, okay, x is equal to v naught xt, or x is equal to 120, almost said 50, times 23.9 seconds. So I take that times 120. I get roughly 2,869. So you're going to need to start around, well, you need to drop it roughly around 2,900 kilometers before you even get there. To give you a scale factor, let me see here, 2.868 divided by 1.61, around 1.75 miles before you actually get to the target. What is 3 kilometers? That's around 1.9 miles above. So, anywho, you'll have to drop it significantly ahead before you get there. Okay, so let's do a slightly different problem and let's do a proof. Because I know proofs are great and you think that too, so we're just all going to do proofs and everyone's going to be happy. Plus, I like doing proofs, so yeah, it's fun. So let's say there's a softball player, and I looked this up at one time. 60 miles an hour is roughly the top speed, so 26.8 meters a second. What angle will she need to have in order to hit a target 40 meters away? And we'll assume that the target is the same height as the player. So I sketched a little sketch or doodle here. Basically, we throw it up and hits here. The initial height and the final height, and I did that backwards, they're going to be the same. So that means, and that we'll get back to this here in a second, that your change in height, your y, overall is going to be 0. More on that later. All right, so we're trying to find angles. So we know that we have x is equal to v naught xt. I'm going to make a substitution because initially we said that v naught x is always going to be v naught cosine theta t. Oopsie. If that kind of got ugly right there. Better. Okay. Well, I don't know time, and I don't know theta. All right, let's look at the y equation. And I'm going to do some craziness here. We have y equals v naught sine theta t minus 1/2 gt squared. Okay, all sorts of new crap. What did I just do? V naught y is going to be v naught sine of theta, as it's always been, at least this chapter. And my arrow sucks. Now my arrow's a little bit better. And then my other thing is g. Well, we know that in free fall it's always going to be a negative 9.8 meters a second squared. And so for ay, I made it g. And then I made it negative 9.8, or negative g in this case, because it's pointing towards the center of the Earth. G is always going to be a positive value when you use it. However, the situation may need to dictate that it's going to be negative, in which case it is, because it's going down. Okay, well, as I told you earlier, that the y, the overall change in height, that's going to be 0. So I'm going to move this over, and that's going to give me g over 2 t squared is equal to v naught sine theta t. All right, you're thinking, oh, something's going to cancel. You're absolutely right. T's are going to cancel. Yes, we got that done. All right. So where does that lead me to? Okay, so that's going to give me, and I'll move this around a bit. That's going to give me gt equals 2 v naught sine of theta. Okay? Alright, so there's many different things that I can do here, but I'm going to have room here. I think I do. From above, remember that x was equal to v naught cosine of theta times t. So we remember that. And the thing is here, what I'm going to do is I'm going to make a substitution. I know that t is going to be x over v naught cosine theta. So that means that gives me g x over v naught cosine of theta. And so that's for my t. And I put in parentheses to say, hey, I made a substitution. And that's equal to 2 v naught sine theta. Okay. Let's move v naught cosine theta over the other side. So that gives me gx is equal to 2, let's write it out this way. V naught squared 2 sine theta cos theta. And I'm going to put boxes around this because One of you is thinking, trig, that looks familiar. Well, it is. From trig, you should remember that 2 sine theta cos theta is equal to the sine of 2 theta. How do we get that? Well, I'm just proving this equation. I don't want to prove this one as well. Otherwise, this lecture is going to be a lot longer than you're going to want to watch. So, you learned it in trig. Good times. Sine 2 theta. Let's make that substitution. Let's make it happen. I'm running out of room here, but that's cool. All right, so that gives me, I'm going to move my x to the other side. That gives me move my g to the other side. So that gives me x is equal to v naught squared over g sine of 2 theta. So this is, sometimes you'll see this written as an r or sometimes an x. Basically, we call this the range equation, or I've always called it that. Range EQ. Basically, this works for a delta y of 0, meaning you have to start and end at the same height. Okay, so that's one of them. Another thing is the max angle can't be larger, so we'll just say max angle is 45. So it's also basically a maximizing equation, because where did I get 45, you ask? Okay, well, the sine of 2 times 45. 2 times 45, that's 90. Sine of 90 is 1. What does that mean? Well, we're going to make that application right now, because this is kind of important. If my max angle is 45, that gives me the v naught, well, let's just write this part out. That means sine of 2 theta is going to be, in this case, this whole thing's going to go to 1. And so at 45 degrees, you're at your max range. Meaning, if I build myself a balloon launcher or a poop cannon, why a poop cannon? I don't know. That's just what came out of my head. And I want to maximize my range, then 45 degrees is going to get my maximum range I can possibly get. Which makes sense. Because if I were to draw a little, I don't know, right angle, then if you want to get your maximum range, you're going to split it and bisect it. And when we bisect it, we get 45 degrees. So not only does it make sense physically with the physical equations, but it also makes sense geometrically. So your maximum range would be 45. So anyhow, long little spiel on how to get this problem. You will not need to do this every time. I only do some proofs to kind of teach you that this isn't all magic. I don't just, pull something out of who knows what and magically I get an equation. It's all based off of sometimes assumptions, the problem, the situation. Physics is literally just like 5 or 6 equations, and you're just using them in different ways and building on each other. And so this is one of them. So to solve for it, we know that our range is 40 meters. So 40 meters is equal to, and we know that our speed was going to be 26.8 meters a second squared over g. Now, remember I just kept saying over and over again in this chapter, g is always a positive value. When you plug in the g, you plug in 9.8 meters a second squared. Well, you say it's negative, it does go to the center of the earth. And guess what? When I set up the problem, I knew, where'd it go? That it was going towards the center of the earth. So I made the fact that my vector was going downwards. And it's already been taken care of. You just plug in a positive. All right, and then sine of 2 theta. So, all sorts of good stuff here. Let's see here. You get meters squared over a meter and a meter. So meter squared over a meter gives you a meter, but then the meters cancels out. Yay! And then seconds squared also cancels out. So we're unitless, and that's good, because when we are trying to find an angle, we don't want a unit in there. I don't even know what that looks like, because I've not even thought about what that looks like until now, and I don't think that's possible. So, anyways, so I'm going to take 40. I'm going to do this in steps because it might have been a while since you've done an evaluation of trig like this. So I'm going to take 40 multiplied by 9.8 and divide that by 26.8 squared. And that's going to give me, I'm going to round it to 0.546 and carry it one digit more than I probably ever should. So I have 0.546 equals the sine of 2 theta. So then I have to take the inverse sine of 0.546. And when you take the inverse sine of this side, it cancels out your sine. And so that'll be equal to 2 theta. So when I take the inverse sine of that number, I get 33. I'm going to round it to 30. Ooh, that's a bad 33. 33.1 is equal to 2 theta. Divide both sides by 2. And that gives me roughly 16.5. And that's a really bad equal sign. And I know. That's a really bad 0.5. And I know. There, much better. So our angle is going to be 16.5. So if you get a problem where it's starting and ending at the same height, you could just literally just use this little bugger. If I could circle it. Got it. Circle. Stop it. Stop it. And I cut off my 2. Yes, I know. I'll fix it. Ha! Did. So you could just use that equation when you have it starting and end at the same height. And then you're thinking, well, what if it doesn't start and end at the same height? What am I going to do then? Okay, well, I'm going to do a problem about that. And that's what's going to happen now. 2 roosters get into a fight on the edge of a cliff in Hawaii. Last time I went to Hawaii, there were chickens everywhere. And I asked them, what's up with the chickens? And they go, they're just there. And I'm like, okay. I don't know much about it, but they're just everywhere. They're in the woods. They're in the parking lot. They're everywhere. So I did a problem about them. Anyways, so 2 roosters get into a fight on the edge of a cliff in Hawaii. An eye is ejected, because why not, at 13 meters a second at an angle of 33 degrees above the horizontal. Let's assume the cliff is 90 meters tall. About how far will the eye land from the base of the cliff? All right. So from this cliff right up here in Hawaii, it's a pretty state, but God, is it humid. Oh, it was brutal. And everything is outside. It's like, oh, the weather's great here. Let's be outside. And I'm like, oh my gosh, I can't stay in humidity. And yeah, there's a breeze kind of near the ocean, but to be honest, it's not nearly as strong as the breeze in Kansas. Yes, I wanted to be in Kansas over Hawaii. I know. Anyways, so let's draw a pretty picture, because that's what we're here for. We're actually here to learn physics, but pretty pictures are part of physics. So we're going to be 33 degrees above the horizontal. So that's this little inner angle here. And it's going to go woo and land on the ground here. All right. Okay, so remember, I'm going to redraw this because I haven't done it in a while, but I think it would be always a good review. Your V naught is at the angle, and so you have to break it down to find your components, which will be V naught Y and V naught X. And so that's what we're going to do first, because if you don't know what else to do, do this first, because at least you got something going on for you. All right, so V naught cos theta is going to be my V naught X, and I should probably write that out, what that actually is, because that helps. Or at least students have told me it helps, so let's do that. So 13 cosine of 33. Make sure you're in degrees, not radians. We hate that crap around here. All right, so we'll say 10.9 is my horizontal velocity. And now we're going to do V naught sine of theta for V naught Y. And that's going to be 13 meters a second sine of 33. So 13 sine 33. 7, we're going to say 7.1. Just for simplicity's sake. All right, so I've got my horizontal and my vertical components of the velocity. Some things about this problem. From earlier we talked about, we know that our vertical velocity at the highest point, Vy, is going to be 0. But I'm not necessarily going to need that. Um, and I'll show you. Well, okay, we want to get horizontal distance, right? So we would use x equals v naught xt, right? But I don't know t and I don't know x. So two unknowns. So let's think about our y equation. That'll be y is equal to v naught y, which is going to be 7.1. And then that'll be 7.1t. And since I know gravity's acting, I'll go ahead and put the negative for the 9.8. What's going to come soon. So minus 1/2 of 9.8 meters a second squared t squared. And I think I gave myself a whole slide to work on this, but I guess I'm just going to work within these confines. Okay, so, and I wrote y, but the thing is, I actually know what y is. It's going to be a negative 90 meters down. So I'm going to plug that in. So it's negative 90 meters is equal to a positive 7.1, since it's going up. Since let me find it here, our vertical velocity is clearly going to be positive. And then minus 1/2 of 9.8, which is not 4.9. That's a terrible 4.9. Negative 4.9 meters a second squared t squared. So, quadratic, you're saying. Yes, you are right. I'm going to drop the units because I've always done that for some strange reason. I feel like it helps. Maybe I'm just being oversimplistic, but maybe it does. Well, that's what we're doing. And then when you bring that 90 over to the other side, that's going to give you a positive value. So, next up, let's do some quadratics. Everyone knows how to do the quadratic equation, I hope, because it's something you should be born with and die with. There are certain equations you should know upon your deathbed, and the quadratic is one of them, in my opinion. There's other ones that you're not going to know, like the Euler-Lagrange equation, which is incredibly important, or Schrodinger's equation, but at least know the quadratic when you die. That just please, just do that for me. Just do that for me. So, it gave me an error. What are you doing to me? Oh, it deleted everything. How terrible. I'm usually a lot faster at doing this, but not today. No siree. Positive 90. And I said that in meters, didn't I? I better have, because I'll be mad at myself. So you get two roots. You get a negative and a positive. Obviously, we take our positive root. And so that gives me a time of 5 point, we'll say around 1 seconds to round it. So that's the complete air time. So that'll give me the time it takes to get from here to here. So then I just plug it into my x equation. And so I say, okay, x is equal to v naught x, which is our horizontal velocity component. It's 10.9. And then t, 5.1. And then I'm just going to multiply that by 10.9. Exit, 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 menu. It's a bad 5.1. Sorry about that. I'm getting 55.6, we'll call it. Pretty far, actually. Luckily, these things don't happen that I know of, so we're good to go. So it's going to travel 55.6 meters horizontally. There are all sorts of things that I can do with this. Let's say I asked you for, well, how far has it gone horizontally when it reaches the apex of its trajectory? Well, the apex of its trajectory is right here when it stops. Basically, I would find the time it takes to get up there and then plug it into x equals vox t. So for most of these problems, you're always going to have two different equations because you have two unknowns and you need two equations. If you have three unknowns, you need three equations and so forth. So, okay, slightly different problem with kind of different parameters here. Kind of give you backstory here. This is Pawnee Butte. It is 300 feet tall, roughly. Which is around 91.5 meters. And you can find it, it's a really bad 5, in northeastern Colorado. And there's a little trail you can take, and you go woo, 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 and you can hike there and have fun. But anyways, it seems like a nice flat butte to do a problem about, so that's what we'll do. All right, with what velocity would a golfer need to impart upon a golf ball if they hope to hit at least just barely, just to the very top of Pawnee Butte? The initial angle is 45 degrees. All right, so kind of walking you through this. Couple things we do know. This time we know our theta. Well, we know that normally, but we don't know V naught. We also know that our acceleration is a negative 9.8, and in difference or contrast, there's the word I'm looking for, to the last problem, our y is actually 91.5, a positive 91.5 meters. So normally we might try to use the y equation, and I'll write out in its long form. So v naught sine theta t plus 1/2 ayt squared. Problem is we don't know time and we don't know v naught, so that's not going to work. We also have the Vy is equal to V naught sine theta plus Ayt. And we do know Vy, actually, because if I'm going to, golf a ball, I guess that is the proper term, and I just want it to just at the top, and that's a really highly exaggerated angle of 45 degrees, by the way, then I know that at the very top right here, I really didn't do a good job with that. That's pretty terrible. Pretty terrible. Let's do this. Also terrible. Try this one more time. There we go. I know that the vertical velocity at the very top of the apex is going to be 0. So I do know that, but what I don't know is V naught and T, so I'm kind of in the same boat. There is an equation we haven't used yet. We are going to use, and that is Vy squared is equal to V naught y squared plus 2ay delta y. I introduced this at the very beginning of this whole lecture, and I haven't used it since. Well, now we're going to. This is 0 because we know if we're just hoping to hit the top, it should be 0. V naught y I will write out in a larger form and move this stuff to the other side. So that gives me a negative 2. And ay is negative 9.8 meters a second squared. And then delta y is going to be 91.5 meters. And then that's equal to, and I'm really getting tilted here, V naught squared, and then that'll be the sine of 45 squared. Sorry about that. I don't know why I got tilty, but okay. So the negatives cancel out, which is good because we're going to have to find V naught squared. Sine of 45, if you recall, is going to be, what is that? 1 over, well, let's do it in decimals, 0.7. And then you'll have to square that. So you sine the 45, and then you square that value to get a even 1/2. So I'm going to write this down here, a little bit better job than what I did right there. That's going to give me, let's see here, 19.6 times 91.5. It's going to give me 1793.4. So that's going to be 1793.4 meters times a meter is a meter squared per second squared is equal to V naught squared, and then the sine of 45 squared is going to give me a clean 1/2. Okay, so multiplying both sides by 2, I'm going to carry this out an extra step. I'm not sure why, I guess because I want to show you the units. So that gives me roughly 3586.8. And then that's meters squared per second squared is equal to V naught squared. Notice it's meters squared per second squared, and when I square root that, it's going to give me a unit of meters a second, which is the appropriate unit that I wanted all along. So I root the crap out of it, and I get 59.9 meters a second. It's actually a reasonable velocity. Probably higher than I could do. I'm not a golfer, but maybe one of you can be. Or could do that. All right, so that's my initial velocity. Yay. All right. How far away would the golfer need to be from the base of the cliff? Okay, so back to my picture here. If this cliff wasn't here, it would just keep going and fall all the way down. So what we want to do is find the horizontal distance, x, that it takes to traverse until it gets to the top of its trajectory. And then we can use, Mr. Cursor, where'd you go? There you are. This equation, so which I'm going to write down here again. Actually, I'm going to come to the next page here, so I'm running out of room. Which is the Vy is equal to V naught sine theta. I'm going to write that whole thing out. Plus AYT. This will not give me the horizontal distance, but this will give me the time. And once I have the time, I can plug it into x is equal to V naught cos theta, writing out the whole thing instead of V naught x, and times t. So we're going to use this to find the time. All right, so this is 0 equals 59.9 meters a second sine, and I already forgot my angle. I think it was a clean 45. Clean 45. And it's messy. Now it's better. And it's messy. Now it's better. Okay. Sine 45 and then minus 9.8 meters a second squared t. Put parentheses around it so it doesn't look too messy. Just going to do the best I can on that. Alright, so then times the sine of 45, and then divide that by 9.8. It should take we're going to say 3 seconds to reach the top of the trajectory. So then we plug it into the x equals v naught x t, or x equals v naught cos theta t. So that's x equals 59.9 meters a second cosine of 45, and then times t, which is 4.3. Multiplying that by 59.9 times the cosine of 45, 183 meters. Pretty far away. You can kind of think of as a meter a little bit bigger than a yard. So like 2 football fields. Probably not going to happen. Alright, so the horizontal distance is going to be 183 meters. And I kind of already answered the third one. I should probably put that as number 2 next time. Oh well. Anyways, yeah, how long will be in the air? Well, it's only going to be in there 4.3 seconds because we're going to suppose it's going to land at the top of Bonnie Butte. And note that this is just to get it there. If we actually really want to get it to land, it needs to be a little bit faster than 59.9. It probably needs to be like 60 if we hope to actually land on the butte. So, anywho, moving on. Relative velocity. It's a way to measure velocity when there are 2 vectors that are not at rest. What do I mean by that? Well, let's say you're driving down the road at 60 miles an hour and you pass a car going at 60 miles an hour in the opposite direction, and then it kind of looks like they're going at 120 if you were at rest, which you feel like you're at rest because you're just in your car. And as long as you have the air conditioner on, you know, you don't even really notice anything in terms of that you're even moving. You only notice that you're moving when you accelerate, but when you're at a constant speed, you don't know it. It's kind of hard to explain that because if you're in a car, there's always I'm going to call them micro accelerations that you can kind of feel when you're moving around in a car. Same thing with a bus, definitely with a train, but if it was smooth, think airplane, it's almost smooth enough that you don't even notice you're moving. So, if the vectors are in the same direction, you subtract. What does that mean? Okay, well, let's say you are going 75 miles an hour and you pass some guy going real slow at 60 miles an hour. then there are two things. So this is you, and this is, I called it that guy. Okay, so that guy, should have come up with a better name than that. That guy, relative to you, is negative 15 miles an hour. If you didn't know you were moving, you would pass that guy, and it would look like they're moving backwards relative to you. And then you, relative to that guy, just put REL, is 15 miles an hour. So a positive, because you passed him. In either case, we subtracted one from the other. We either subtracted 60 from 75 or 75 from 60, depending on whose point of view we were trying to look at. So that's kind of a term that we use a lot, is relative to this and relative to that. So if they're in opposite directions, we add them, as I demonstrated earlier when we went 60 miles an hour and where'd my cursor go? We went 60 miles an hour in one direction, 60 miles an hour in the other. It looks like they're going at 120. That's why head-on collisions are so bad, because it's the equivalent of you just sitting in a car getting hit at 120 miles an hour. They tend to be pretty drastic. We can also apply this to 2D motion. I'm going to do a problem first based on a 1D or one-dimensional motion problem, and then we'll do some two-dimensionals as well. But really, the relative velocity problems shouldn't be too bad. They're kind of some of the easier stuff. All right, so this time I didn't name him just that guy. I actually gave him a good name. I finally spelled it correctly this year. Ryan Righteousness is paddling on the Arkansas River, or sorry, the Arkansas River as we call it here. I'm from West Virginia, so I don't always say it right. If Ryan is paddling at 3 meters a second, a wind is blowing at 2 meters a second against Ryan, and Carney Carnivore on the shore says Ryan is only at 2.5 meters a second. How fast is the river moving, and in what direction? So, problems like this you kind of have to draw out. I'm going to assume it's going to the right, so I'm just going to draw arrows, because sometimes it makes it easier. So Ryan's velocity is 3 meters a second, and we're assuming they're all interacting perfectly. Meaning most of the I'm doing one on the river, which is okay, but like you think of moving walkways in the airport, that's got a very constant speed and affects the speed of view. So 3 meters a second, wind 2. So I'm gonna say, okay, here's a 2, and that's gonna go in the opposite direction. And then there is a current, which I would normally put as a dashed line, which we don't know. And then the overall is a positive 2.5. So I'll try to make that a little bit smaller than I made my 3. So basically, and this is going to be more important once we get to forces, you take everything going to the right, subtract everything going to the left, and then that's what equals to what's left over. What's left over in this case is going to be 2.5. So, okay, I take my 3 meters a second. That is a really bad M. Let's make that M better. Yay. Minus the 2 meters a second. Plus some current. You always say plus. It could be moving towards it, could be moving against it, but that doesn't matter. We just say plus the current. And as long as our directions are held constant, meaning, well, I said it was 2.5 in the end, going in the same direction as Ryan. As long as we hold that constant, then your answer will come out to be the right sign, whether it be positive or negative. So that's equal to a positive 2.5 meters a second. So all we really have to do is solve for C. So that'll be 2.5 minus, looks like to be 1. So our current is going to be 1.5 meters a second. So the fact that it's positive says it's going in the same direction as Ryan. If the answer would have come out negative, it would have been, the current would have been moving against Ryan. So Okay. Okay, so this isn't in your book, but I kind of think it's important, particularly when we get to physics 2. I haven't taught physics 2 in a while. Um, you will learn about electric and magnetic fields and how they're intertwined. But for now, I'm doing this just to show you kind of one pivotal, um, not thought, but one pivotal um, thing, tangible thing to take home. And that is that acceleration is the same in all reference frames. What do I mean by that? Well, let's show you. So, we got a cameraman on a truck, travels west at 10 meters a second while videotaping a cheetah moving west 20 meters a second faster than him. The cheetah stops, turns, and runs at 25 meters a second east as measured by a bystander in a period of 2 seconds. We are going to find the acceleration according to the bystander and the cameraman. All right, this needs to be drawn out, otherwise we'll never solve. Never, never solve. Never, never solve. Okay? All right, so I'm going to draw a pretty truck. Pretty truck. Pretty truck, pretty truck, pretty truck. Okay. Here is my truck. And I need a cameraman. I don't know what a camera looks like. Close enough. Okay. We know that the truck is traveling west at 10 meters a second. And also, I need to draw my bystander. And he's like, oh, what the crap is going on here? I don't understand. So, all right. 10 meters a second. Now, so, I'm going to write this out here. So, C's truck at -10. Why did I put a negative? That's because it's going west, and we're going to need to factor that in a little bit. So he sees the truck moving at -10 meters a second. Okay? Keep that in mind. The cameraman is videotaping a cheetah moving west 20 meters a second faster than him. So, we have a cheetah, and his camera's pointing in the wrong direction, and I'm aware of that. Yeah, that's not really a cheetah, I'm fully aware. Close enough. So, we see that the cameraman sees that the cheetah is moving 20 meters a second faster than him in that direction. So, I'm going to write this out here. Sees cheetah at 20. And since it's moving to the left also, we're going to say -20 meters a second. Okay, so if he sees the cheetah moving at -20, and they're already moving at -10, the cameraman and truck crew, then bystander sees cheetah at -30. These numbers are a little bit unrealistic, FYI, but it works for what I'm doing. Cheetahs can't run that fast. So, sees cheetah at -30. Actually, they may be close. No, they can't do 30. No, I don't think so. -30 meters a second. All right, so those are our two different things going on here. So, cameraman and bystander are seeing two very different velocities of the cheetah. Same direction, but two different velocities. Okay, so then the cheetah says, oh, screw this crap. Screw you guys, I'm going home. And then it goes and turns around, and it does this in a period of 2 seconds. And then it goes 25 meters a second. As measured by the bystander. So the bystander now sees cheetah at 25. Okay, that makes sense. But what about the cameraman, you ask? Well, afterwards, the cameraman, since the cameraman's still traveling at 10 meters a second in the opposite direction, and now the cheetah's 25 meters a second also in the opposite direction, that's going to seize cheetah at 10 plus 25, 35. And a positive 35 meters a second because now it's moving to the right. So that's our setup, and this gives us the speed of the cheetah before and after the turnaround with respect to both the cameraman and the bystander. So my setup is at least ready to go. All right, so what do I need to do? I'm trying to find acceleration. Well, our the definition of acceleration is the change in velocity over the change in time. So first, let's figure it out with the bystander. So by. A-B-Y for bystander. All right, so it'll be final speed minus initial speed. According to my notes, sees cheetah at a positive 25, so that'll be the final speed, minus the initial speed, and the initial speed of the cheetah was negative 30, so that'll be minus a negative 30, and then that's all divided by 2. So that becomes 25 minus negative 30. 25 plus 30 gives you a positive 55. We divide that by 2 to get 27.5 meters per second squared. Okay, well, let's do it for the cameraman. So ACAM, or just AC. Just AC. I don't want to write out any more letters. AC. All right. So according to my notes up here, sees cheetah at 35 after the turnaround. Initial sees cheetah at negative 20. Divided by 2. So 35 minus a negative 20 gives me a positive 55. 55 divided by 2, surprise, surprise. Acceleration according to the cameraman, 27.5 meters per second squared. This has pretty interesting implications. While the cameraman and the bystander saw different velocities of the cheetah at different points in time, they saw the same acceleration of the cheetah. So while people see different velocities depending on their reference frame, everybody sees the same acceleration no matter what reference frame you're in. Whether you're in a truck, whether you're a bystander, whether you're a deer running by at 10 meters a second, whether you're in a bus walking backwards that's traveling forwards, it doesn't matter. The point is, everybody sees the same acceleration, but we all see different velocities, which is kind of hard to accept because it's kind of hard to see acceleration, but the math holds, and more importantly, the physics holds. So no matter what you do, every person sees the same acceleration, but they're definitely going to see different velocities depending on their reference frames. All right, let's do a different problem here. I can write, that's good. Let's say you have a bus traveling at 60 miles an hour, 26.8 meters a second, to the right. The terminal speed of a raindrop, it's around 9 meters a second, depending on the size and shape, but I think that's like the average if I remember correctly. If the raindrop is falling vertically to the ground, then at what angle from the vertical do the drops appear relative to a passenger on the bus? When I was looking this up and looked for a picture of a bus, I did find this one, which was an advertisement at a Copenhagen zoo on a bus. They've got a lot cooler buses, I suppose, than we do. Anywho, so let me draw a little picture here. We know that the bus is going at 26.8. And we have to draw head to tail vectors, and then we know that the raindrop is very small at 9 meters a second. So what we want to do is find this little angle here. And you're thinking to yourself, no way, raindrops are not that, slanted. When we drive, they're obviously going to have some slant. And the faster we go this way, the more the slant. But in this case, they're actually asking for from the vertical, so we're going to look for this angle. But we're going to do that to get this angle, and then we'll just take the complementary. So anyhow, you just use inverse tangent. It's a rather simple problem relative to the next one, I think. So take the inverse tangent of 9, don't need units, yay, over 26.8. Lost something here. So I take 9 divided by 26.8, take the inverse tangent of that, and I get 18.6 degrees. Okay, so this is 18.6, and then we need to take the complementary. So 90 minus 18.6, and we get 71.4, which, depending on how you think about it, kind of seems really high. But it's not as high as you think, because if you're not moving, so let me write this down. If you're not moving, then they're going to appear to be 90 degrees. I mean, that makes sense. It's going to go straight down. Okay, yeah, you're thinking, oh, well, wind, it can push it left and right. We're assuming it's just rain and no wind, just a drizzly day. It would be 90 degrees. But now it's slightly pushed off by 18.6 degrees, so the angle is 71.4 for the vertical. So that's what it means when I ask you that. And it's similar to a problem you have on your homework. I just changed up what we're solving for. So, okay, last one. A creek has a current that is flowing at 3 meters a second to the right, so that's my current speed. You can paddle at a top constant speed of 4 meters a second, so you're not accelerating. You can only go 4 meters a second. You can't slow down, you can't speed up, you just go 4. At what angle will you need to aim your canoe to land, to travel from the cape to the point? Basically, we have the point of brutal retribution right here, and we want to get to the Cape of 1,000 Deaths. And so what we want is to go right across. Well, if this is a lake, we probably could do that, but we can't, because if I do that, then I'm just going to end up drifting off to the side, and I may end up at a cape with a much worse name than Cape of 1,000 Deaths, maybe Cape of 20,000 Deaths. In any case, we'd rather be at the Cape of 1,000 Deaths. I'm exaggerating with the names here, but some of the capes and points have some pretty interesting names that signify, oh, this is an area of death, we should stay away. And I kind of took it a little bit, probably too extreme, but it's what I came up with when I was making the problem. And so what do we want to do? We want to aim our canoe this way. So if we aim our canoe this way, we should just go straight down. And I know that my canoe is going to be 4 meters a second. So that's kind of my hypotenuse. I also know one very important thing. I know that I want my total horizontal velocity to be 0. Basically put, I want the horizontal component, I'll just call it the Vx. Well, that's really bad because I already used Vx. Let's just call it the horizontal component. I'm just going to write it all out so I don't get confusing here. We want that horizontal component to be equal, or the total to be equal to 0, but we want this little horizontal component must be equal to 3, so that we're going to call it hz plus 3 relative to the sign. I know one's going to be plus, one's going to be negative, must equal 0. So basically, make it a little bit more clear here, I want to take my 3 meters a second and then set that equal to my horizontal component, which will be 4 meters a second. My angle is right here, so it's going to be the far side of it, so we're looking at sine. So that'll be 4 meters a second sine of theta. Meters a second cancels. And so I will take, okay, so 3 over 4. Well, that's good, because I had this problem wrong the first time I solved this last year and had to change my numbers. And you get 48.6. So basically put, you would actually, I mean, it'd be pretty steep, to be honest with you. 45 would be like roughly half, but you're going to have to aim it over halfway from the vertical so that you get exactly over the creek to get to the Cape of 1,000 Deaths. So, all right, that is the last slide of this lecture, of this chapter. Hopefully by the end of this week, I will post your written homework and talk more about it. Your test is still far away, and I'm a couple lectures ahead, which is good. I'm trying to get way ahead in the lectures so you can kind of go at your own pace, sort of, with the exception of tests. But I'll talk about that later. As I said, I had like a week to prepare for class, so it's a little rushed. Luckily, I have taught it before, so I have most of the material, but I have not taught it online, or at least putting most of this online, so that's new to me. So, anywho, if you have any questions, I'm available every day, Tuesdays, Thursdays, Jabara 128 from roughly 5. Honestly, I get there around 5. And I'm there roughly 6:50. So if you have any questions, you can do that. You can also email me if you're not comfortable coming in person. That's fine too. I don't really have that much of a preference on whether you come in person. Just make sure you let me know. That's really all it boils down to. So anyways, that's it.